Hi everybody, welcome to the SPCI show. Today we'll focus on our project we've done during our courses.
Nothing is too wonderful to be true if it be consistent with the laws of nature. This quote from Michael Faraday shows us that in this ever-changing world there are some things we can depend on.
Mechanics, biology, chemistry. Scientists always try to explain what they have seen in nature. Well, consider for a moment the Leidenfrost Effect. The Leidenfrost Effect is what you see when a liquid comes in contact with an object that is a lot hotter than the liquid's boiling point.
If the pan's temperature is above the Leidenfrost temperature, which is about 220 degrees for water, the water skitters across the pan and takes longer to evaporate than in a pan below the Leidenfrost point. This strange effect is named after John Gottlob Leidenfrost, a German physician who published a scientific paper on the phenomenon back in 1756.
He explained that past the Leidenfrost point, the bottom surface of the water droplet turns to vapor so quickly that it creates a little insulating pocket under the drop, and pressure from the vapor keeps the droplet aloft like a tiny ladder of a craft. As it scoots around on the toasty surface, molecules of water keep turning into vapor from the underside of the droplet in a process known as film boiling. Many scientists had worked on this subject because this effect is annoying in the industrial realm, when you have to cool some tools or machines. The most telling example is in nuclear power plants. A Leidenfrost effect appears when you try to cool the nuclear bar rods because of the huge gap of temperature between the rods and the cooling water. Moreover, the part of the Leidenfrost effect that's the most interesting to scientists is how the droplet move with so little friction between the liquid and the surface. Even slight disturbances in the vapor pockets, caused by escaping molecules of gas, are enough to send the droplet ricocheting all over the place. The only problem was scientists could only control the droplets when they were above the Leidenfrost temperature, and 220 degrees is hot. With our team, we decided to study this effect on hot liquid surface. Let us show you our experiments and results. Here is our experimental setup. It is composed of a heating plate, a double boiler of peanut oil. We put a drop of isopropanol on the hot bath and film the Leidenfrost drop with a camera on the side. The movie is then treated by a MATLAB code so as to get the evolution of the radius and the position of the drop with the time. A thermocouple probe is maintained in the bath so as to be the most accurate as possible on the measure of the temperature, which is the main variable here. Compared to Leidenfrost effect on solid surface, the one on liquid allows us to work at lower temperature. We obtain Leidenfrost drops from 92.5 degrees Celsius. This is to say 10 degrees above the boiling point of isopropanol. Indeed, the hot surface here is far smoother than a solid surface, so that the boiling is triggered later. We observe two kinds of behavior. Firstly, when the gap of temperatures between the bath and the boiling point of isopropanol is less than 28 degrees Celsius, the drop moves into the container. However, when the gap is higher than 28 degrees Celsius, the drop doesn't move. The next goal was then to characterize those two behaviors. For the static drops, we observe that the higher the temperature, the faster the radius decreases. Indeed, the heat produces more steam from the droplet and thus it evaporates faster. After we studied the dynamic behavior, we switched from a circular bath to a square bath so as to understand the shock dynamics, and we find that the velocity was conserved just before and after the shock, by characterizing its path. This allows us to conclude that the shocks were elastic as the kinetic energy was conserved. Finally, studying the Leidenfrost effect on liquids could be a solution to control the movement of the drops at lower temperatures than those for solid Leidenfrost effect.